Drag force is kind of like friction in that it's going to oppose the motion, and it's opposing the motion as an object flows through a fluid, or an object goes through a fluid. So, in a fluid, basically, is just anything that can flow. So, a gas like air, if we're talking about the skydiver right here, or a liquid, if we have someone swimming through water, they're also going to experience a drag force. So when we have a relative velocity between the fluid and the object experiences a drag force. That drag force, like I said, opposes the relative motion and points in the direction the fluid flows relative to the body. So, for example, this skydiver's falling down, the fluid is flowing past them, right? The air flowing past them this way. Drag force is pointed behind the skydiver or upwards if we're looking at that relative to the ground. So, like I said, when someone's falling through the air like a skydiver, that drag force is equal to what we call air resistance. So, this is the same thing basically, but drag force can also be in the water as well or any other fluid. So, the equation for drag force is a capital D for drag is equal to 1/2 C rho. That's a fancy P, but it's actually rho. It's a Greek letter, times A, the area, times V, velocity squared. So, like I said, capital D is the drag force, capital C is the drag coefficient, and the typical values for the drag coefficient range from zero point 0.4 to 1. Obviously, the higher the drag coefficient, the higher the drag force. And this has to do with the shape of the object. And this is like a given kind of. They'll, say the drag coefficient for this is blank. All right. And the more aerodynamic something is, the lower the drag coefficient. Rho is the density of the fluid. So if we're talking about something traveling through the air, that will be the density of the air. If it's something traveling through the water, it will be the density of the water. Obviously, the denser the fluid, the more drag it causes. Capital A is that effective cross-sectional area. This will be the perpendicular area to where the object is moving. All right. And as the area changes, the drag force will change, which is why skydivers, when they change their orientation, so they're either spread out, that area is big, or they kind of go in and maybe go feet first or something like that, that area will be smaller. So it's going to be that area that's perpendicular to the direction of motion. And then last but not least, V is velocity. So we can see the faster we go, the higher the drag force. So if we're in free fall, that drag force will be directed upward. Obviously, if we draw a free body diagram, we have the force of gravity down, the air resistance or drag force upward. That magnitude of the drag force gradually increases from 0 because the speed is increasing. All right. Now, that drag force opposes the downward gravitational force, Fg, like I said, and so we get this equation right here. This equation is from your book, and it does say that up is positive, down is negative. That's why they have d up minus force of gravity is equal to mass times acceleration. Acceleration is the new acceleration of free fall. Obviously, it's going to be lower than negative 9.8 meters per second squared because we have a drag force d that's slowing down that motion. So if you are using this equation with upwards directed as positive, obviously the acceleration is down, so you will get a negative number for this acceleration. Or if you know the acceleration, you have to plug in a negative. Another way to write this equation is saying down positive. You could say Fg minus d is equal to ma. You end up getting a positive acceleration, or you plug in a positive acceleration. And then last but not least, let's talk about terminal velocity. So if a body falls long enough, the drag force will equal the force of gravity. So this is when forces are balanced, right? Which means that acceleration is equal to 0, and we've reached something called terminal velocity because speed no longer increases because, again, acceleration is 0. So this is called terminal speed or terminal velocity. And so to find that, what we can do here is with our last equation, we can set acceleration equal to 0 and we can solve. So since we know that drag force minus force of gravity equals ma on our last slide, we then just plug in the equation for drag force d, and then we can solve for velocity. So what we do here, add force of gravity to both sides. We want to multiply both sides by 2, divide by our drag coefficient, our density, and our area, and then take the square root. So we end up getting the terminal velocity will be equal to the square root of 2 times the force of gravity divided by our drag coefficient times the density times the area.